Having introduced the Moivre's theorem, we can now begin to talk about what the roots of a complex number are going to be. So we know that if we have some complex number set, we can raise it to the power of n, and that's going to be the same as Rn cosine n theta plus I sine n theta, which is the same as its polar form r to the power of n e to the power of I times n theta, right? So that's what we derive from the Moivre's theorem. So let's say we were interested in finding the roots of a complex number, so something like z to the power of half. Now obviously we can assume that we're going to have the same formula, so let's have r1 half, and this is going to be I to the power of theta over 2. And you might think, is this correct? Because it seems a little bit too easy that it would actually be this expression, but you would actually be partially right. This is actually how you would find the complex roots of a complex number. And that's a really interesting thing because it's just a direct application of the Moivre's theorem and also the Euler identity. But for now, what we need to know is that obviously when you're taking roots of a number, you don't get just one root. You get a number of root equal to whatever root you're taking. So if you're taking the square root of something, you're going to get 2 roots. If you're getting the third or the cubic root of a complex number, you're going to get 3 roots. So you're going to write 1 over 3 ei theta over 3. So how can we generalize these results for all those roots that we have? Well, there's this little formula here. So if we have a complex number to the root of 1 over n, or to the root of n essentially, this is the same as saying r to the power of 1 over n times e I to the power of theta plus 2k, so 2k pi over n, and this is going to be between these curly brackets, because essentially what we want to represent here is a set of values. So the set of values here is going to be equal to the number n. So you can imagine that if we're taking a square root, what we're going to do is we're going to list 2 values. So let's say value 1 and value 2. So we're going to list them like this. So that's why I use this curly bracket notation here. So what is this new term that we introduced? That k. Well, k is just an integer. So k is a positive integer. And it is actually going to go from 0, 1, 2, all the way to n minus 1. So that's just an integer. So that's telling us that for each of those, so if n is equal to 2, then we're going to have k equal to 0 and then k equal to 1. So each of those values of k are going to give us a different value for the root of a complex number. And then n is just going to be the same. So basically we're just going to be adding that factor of pi to it. And just to illustrate how this works, this is a really powerful formula. It's a really useful one. Let's have the complex number z equals to 1 plus I. And let's say we're interested in finding the square root of that. So let's try and find the square root of that complex number. The first thing we need to do is find the polar form of this. So this is the same number that we worked with in the video where I explained what the Moivre theorem was. So this is going to be 1 and 1. That's pi on 4, that's the angle. And the magnitude is going to be square root of 2. So this is the same as saying square root of 2 e to the power of I pi on 4. So that's going to be that. And then we can express this as what's going to be this. That's going to be 2 to the power of 1 over 4. And I'm just going to leave it like that because that's essentially going to be our exact form. And here we're going to have 2 sets of numbers. So the first one is going to be the following. If we put it right back into this equation, we're going to have e to the power of I pi on 4, so that's our angle, plus 2k pi over n, which is 2. So this is going to be our general formula. And now if we list the roots, we're going to have 2 to the power of 1 over 4 e to the power of I. So the first value of k is going to be 0. So if we put 0 here, that's just pi on 4 over 2, which turns out to be just pi over 8. So that's going to be pi on 8. That's the first root that we're going to find. And then the second root is going to be the following. So we're going to put k equals to 1. That's the second value. And you notice that 1 is actually n minus 1. So that's the last value of k that we're going to have for this case. So we're going to put that value in here. So 1 is going to add 2 pi to pi over 4. So what's going to be pi over 4 plus 2? That's going to be 9 pi over 4. And then if we divide that by 2, that's going to be 9 over 8. So 2 but remember, there's a little bit of simplification we can do here. It's actually rather transform this to standard notation. Remember that we define our angle from minus pi to pi. So if we have this angle, which is actually 9 pi over 8, it is actually going a little bit over that boundary. So what we're going to have is we're going to have the opposite. So what's going to be 2 pi minus this? Well, 2 minus 9 over 8 is the same as 7 pi over 8. So that's how we are going to express that. That's going to be 2 1 over 4 e to the I pi over 8, just so that it stays within this range here, within this domain. So 2 to the power of 1 over 4 e to the minus I 7 pi over 8. So those are going to be our two roots for this complex number, and we could plot them. We could plot them by finding the Cartesian form first, and then just plotting them on the Argand diagram. But we can actually sketch them. We can sketch these complex numbers by simply taking note that this is just essentially going to be the radius of a circle. So we can plot them on the same circle. We're going to have our imaginary axis here and a real axis. And so if we want to plot this complex number, that's pi over 8. So pi over 8 is equivalent to what? That's going to be something like 22.5 degrees. So that's going to be around that. So I'm just going to sketch it. I'm not going to make it to scale. And then the radius of that is going to be 2 to the power of 1 over 4. So that we're going to have some values here. I'm not going to find it, but that's just to show you what that would look like. And then if we want to plot this one, well, what's that going to look like? That has to be essentially located here, because we already talked about how that angle is going to be going over that limit for pi, but it's actually, we can represent it as coming from the other side. So this is going to be minus 7 pi over 8. And it's going to have the same magnitude. So both of these are actually going to be collinear, and they're going to form the diameter of this circle. And that's a really nice thing about the roots of a complex number, is that they're all going to have the same magnitude. So you can always plot them on a circle, and you're always going to have an equal number of complex numbers that is going to be spaced apart by the same amount of angle, because we notice here, what's the separation between them? Well, how much of a rotation we have here? We have 2 pi degrees or 2 pi radian available in this whole plane. And we have 2 roots here. So what's going to be the angle between them is going to have to be 180 degrees or just pi, because we have to divide that particular 2 pi radians that we have available into equal quantities for those. In a similar way, if we had the cubic roots of a complex number, we would get something like this. We would get a circle, and the radius would be the same for all of them, but then we would have to basically just split it up into equal portions. So the angle here between those two is going to be theta, that's going to be theta, and that's going to be theta. So the really nice thing is that for any number of complex, you're always going to have the same angular spacing between them, between the points. And you can pretty much draw a shape out of them. You can draw a polygon, and it's going to have equal sides, and it's going to have equal internal angles. So if I tell you find the fifth root of a complex number, you would apply the same formula here, but you would have 5 values, and each of those values would be plotted on the Argand diagram as follows. So let's say you have 5 values. That's a really ugly circle, but just bear with me. You're going to have a circle. So if you have 5, you're going to end up with a shape like this. So let's try to accommodate 5 points here somehow. I'm gonna try my best. It's not going to be very pretty, but essentially you would have the same spacing between them, and in the end you would end up with a pentagon if you join the points that they occupy in this plane, and then the internal angles are going to be the same. So that's a really interesting thing that the roots of complex number follow, and it applies for any complex number. If you have 10 roots of a complex number, then you would have 10 poles, and they would be equally spaced from each other, and then you would get another polygon. So that's just to show you the connection between this and that formula that I just showed you. So that's a really interesting thing, and essentially what this allows you to do is you can find the roots of any number, not just an imaginary number, but one that has something like just a real part. So let's say our number is just 1, and we want to find the fourth roots of unity. How would you do that? You might think, well, 1 is just 1, there's just going to be one root, but not really. If you look at it from the point of view of complex numbers, you can actually have 4 different values that would give you that. So if we make this into a polar form, so this is just going to be the same as saying, well, this complex number only has a real part, right? It has no imaginary part. So the angle has to be 0. And then what is going to be the magnitude? The magnitude is going to be 1. So this is the same as saying e to the power of I0, which you know is just going to be 1. But we're interested in expressing it in polar form so that we can apply the formula. So let's have a look at what this would look like. So if we want to take the 4th root of that, then we're going to end up with this. We're going to have the following. We're going to have e to the power of I, so our angle is 0 plus 2k pi over 4. So let's see what values we have of this. And we know that we're going to have 1 as our radius or our magnitude. So we're going to have, the first one is going to be, so k is going to go k equals 0, 1, 2, and 3, because we want it up to n minus 1, so n is 4 in this case. And that's going to be the same as 2k pi over 4. Actually, I'm just going to simplify that. So let's have the first value. That's going to be for k equals to 0, so that's just 0 radians. And we can express it in quotation form later on, but I'm just going to focus on this at the moment. Second value is going to be k equals to 1, so that's going to be I pi on 2. E to the I, so that's going to be what? K is equal to 2, so that's going to be pi. So you notice the pattern here. There's actually an increase in the angle by pi on half, because we're adding pi on half. So half pi here, half pi to that one, and then this one has to be 3 pi on 2. But remember, we want to express it in terms of a within the range minus pi to pi. So we can actually rewrite this one as minus half pi. Let me just erase that, and this is going to be minus pi on 2. So those are going to be the 4 values of our roots. And now if we proceed to plot them on the Argand diagram, so let me just draw them here. What are we going to have? Well, we have radius equal to 1, and we have the following angles: 0, pi on 2, pi, and minus pi on 2. So that means that we're going to have, the first one is going to be located here, the second one is going to be here, the third one is going to be located here, and then the last one is here. So we start with this, we have another one here, another one here, another one here, and then we're going to draw a circle, so they're going to lie on the same circle, the same circumference. And if you notice, if you join these points, you get a rhombus or a diamond shape, or if you look at it from a tilted angle, it's just a square, and they're going to have equal sides and equal angles here. So that's a really interesting thing. So what that tells us is that the fourth roots of unity, which you would think, well, it should just be 1, but it's not quite. It's actually going to be the following values. You're going to have 1, so that's the first one. The second one is 1 in the imaginary axis, so that's just I. The third one is going to be -1 in the real axis, and the last one is going to be -I. So even though this is technically a real number, we were able to find the fourth roots by using the concept of complex numbers and using this formula I just gave you. So this is just a really interesting application of complex numbers. And in the next video, we're going to keep talking about complex numbers. We're going to be looking at a little bit more complicated examples of what you can use with complex numbers. So for example, let's say you want to evaluate the following complex number, natural log of 1 plus I. Now obviously we're going to have to use a different kind of technique with that, and that's what we're going to explore in the next video.